and just making photons is quite common. This is one way in which positrons actually have been taken out of the mix of things. They've been kind of annihilated and gotten rid of, whereas there were other methods of producing electrons. So electrons were able to stick around, be produced, be a thing that we know and love, whereas positrons we're less familiar with, right? Because they're not as abundantly found in nature. They're not as common. We know that it's the weird antiparticle partner of the electron, but how often do you really meet a positron, right? So that's sort of the thing with the antiparticles. Physicists have recognized a pattern among these particles displayed in table 1.1. Okay, we will take a look. All I see is the names of the particles, their masses, and whatnot. Okay, each family, the particle or the matter particles neatly fall into 3 groups, which are often called families. I think I just mentioned the families, and hopefully that's what he's doing too. Each family contains 2 of the quarks. Oh, I see. The 3 families of fundamental particles and their masses in multiples of the proton mass. I'm going to show you the table, so don't worry, but the values of the neutrino masses have so far eluded. When he wrote the book, I think they did not have neutrino masses yet. Or they maybe just had error bars or something. Oh dear, I see. Okay, let's see what he's saying. I don't know if I would, organize the particles quite like that, but okay. Let's just see what he's saying. Let's see what the string theorist has to say about particles. Each family contains 2 of the quarks, an electron or one of its cousins, and one of the neutrino species. The corresponding particle types across the 3 families have identical properties except for their mass, which grows larger in each. I see. Okay. That all of this is to say there's electron, neutrino, up quark, down quark, right? So electron, we know what that is. Electron, neutrino, it's a type of neutrino. Up quark, down quark, those make up protons and neutrons. Then we come over, we've got muon neutrino, charm quark, strange quark. So it's kind of like just saying that, okay, leptons, in the leptons we have muon and muon neutrino. We have charm quark and a strange quark, which are heavier than the up quark and down quark. Then we come over to the 3rd column. We have tau neutrino, top quark, and bottom quark. And these are, again, all heavier than the middle column. So the columns basically just get kind of heavier in the masses of these particles. But tau neutrino, those are leptons. So this is not really how I organize things, or I would organize things. I would just say that leptons are the electron, muon, tau, and the electron, muon, and tau neutrinos. Those 3 flavors of neutrinos, those are the leptons. Quarks are up, down, charm, strange, top, bottom. And then I would mention the bosons, which are the 3rd family of particles. I wouldn't really do this table, but this table does give you the masses of the particles. And yes, like he said, those masses are increasing when you go from electron to muon to tau. And I think from electron neutrino to muon neutrino to tau neutrino, and then up quark to charm quark to top quark, and then down quark to strange quark to bottom quark. So these things are heavier. Top is heavier than charm, is heavier than up. Bottom is heavier than strange, is heavier than down. Okay, or you could just have a different way of organizing the particles and kind of just look up their mass, because not everybody's going to remember every particle's mass, because there's so many particles. So it's all good, however it works. The upshot is that physicists have now probed the structure of matter to scales of about a billionth of a meter, and shown that everything encountered to date, whether it occurs naturally or is produced artificially with giant atom smashers, consists of some combination of particles from these 3 families and their antimatter